uh, have been ongoing since last week. Today we'll look at some of the hardware specifications and um, uh, some part of FPGA, and we might also look at uh, our first app as well, uh, permitting time. So let me get started. Hardware overview. So basically, this is like old hardware overview, not the. There are some new components with newer ports. So we won't be covering that. This is like the traditional hardware that we have had on 730 platforms. All switches have SFP plus ports, basically 100 meg to 10 gig. 48 port switches are 1 RU, and then there are a couple of 96 ports as well, platforms, which are 2 RU. All are based x86 64 CPUs running MOS. All of them have onboard SSDs, which means that all the memory is non-volatile. So basically, even if a switch reloads, none of the logs are uh, not deleted. Like EOS, in EOS you have only files which are on flash that are saved after reload, but on MOS, all the files which are on SSDs are stored and restored, so we don't really lose logs on reboot. Works with a long list of MSA compliant third-party SFPs. So basically, on MOS, you don't really have a non-supported SFP as such, as long as it's an MSA compliant SFP, a third-party SFP, which has like all the specifications which are standard compliant in this industry. It should just work on MOS. You don't really need a third-party unlock code or anything because it's running MOS, which is older, which itself used to, which never had a SFP of their own, Metamaco. They used to support all the third-party SFPs. So anything and everything works as long as it's industry standard compliant for SFPs. All have dual redundant hot swappable power supplies and fans, similar to any EOS switch. Airflow both forward, reverse. Layer 1 latency 4 to 6 nanoseconds. We have seen this before in previous couple of sessions. And completely non-blocking architecture because it's one-to-one. There is no blocking anywhere as such. There is no drops as such in this architecture. This is like a switch, basically an overview of an image of a 48K.
Yeah, one quick question here. So that third-party transceiver will work without any unlocking command, only if it's MOS, right?
Yes.
Is that the same if the switch? Okay, if the EOS, if it is EOS, then we need again unlock code, right?
Yeah, like any other iOS
Okay,
platform, they'll need unlocker.
okay. If it's only MOS, then okay, cool. Understood.
Yeah,
Thank you.
yeah.
And if they change from MOS to EOS, in that case,
It will need unlock code once it loads iOS.
okay, got it.
This is our a standard M48K switch. We don't, I think this is end of support, end of life now, but it just gives a picture of how a standard Metamarco switch looks. It's very similar to any other 1RU switches. Um, some of the things that are like different is one thing, if you look at the two here, mm, two here that says PPS in and PPS out. Everyone can see it, right? Or do I need to zoom in?
You can zoom in a bit.
And how does it
It's not
They have
possible.
to-
It's okay.
come out?
I think it's fine.
You can see the magnifying. You can see this, right? PPS in and PPS out here.
Yeah.
So that's something that is different than any EOS platforms. PPS means pulse per second. It's a kind of a time source which is used for time stamping on EOS, on 70 and 30 devices. We'll take a look at how exactly it works and what it means when we go through MetaWatch app. But for now, you can just um, remember that there is something called the pulse per second. In means this is where we are receiving pulse from an external device, and out means that the switch itself can provide pulses to another external device. It has its use cases. We'll go through that once when we are going through MetaWatch. But for now, just keep this in mind. Other than that, everything is just standard like any other switch. You have ports, Ethernet management port, USB, LEDs, console port. So basically everything like any other standard switch. Any questions? Um, for inventory, the same output, same command is available as US. You can do show inventory. It will show system information, model, serial number, software image version, system management controller version, description of the platform, mezzanine module information. Not entirely sure exactly what it defines, but it kind of defines if it's about the platform. I'll check exact details on mezzanine, but we again will discuss mezzanine and when we discuss MetaWatch, so we can circle back then again. FPGA information. So it means the FPGA which is installed on the platform. On this one is a M48K. It has Xilinx Vertex 7. There are different FPGAs, and depending on FPGAs, the applications which we can run on that on the FPGA differs. So you have different versions of FPGAs. So we'll take a look at that as well when we discuss the apps. Clock module information. So some of the platforms have inbuilt clocks as well. There are different types of clocks as well. This again is used for timestamping in MetaWatch. PSU information, airflow information. So it's not standard like any other switch. Continued with show inventory, we'll see the SFPs, vendor, part number, serial numbers as well. We also see the storage device, which is available on the switch. Moving on, the naming. So this is the old naming. So in old, they used to call the devices as MetaConnect, MetaMux, MetaProtect, and MetaApp. So these are the platform names. Internal name is C, and these internal name are based on that MetaConnect, MetaMux. Then we have ports range 16 to 96. Some of the older ones like 1632, I don't think we have them anymore. They're end of life. Then we have internal names for FPGAs as well. And these are based on Australian birds. So these are Cassowary, Kookaburra, Emu, and Lyrebird. That also becomes part of the platform name, CKE, and these are based on Australian bird names because it's an Australian company. They named them on the based on Australian birds. Name of the switch is generally internal name, number of ports, and then the FPGA type. So, for example, the M48E, which means Metamux device with 48 ports and EMO FPGA. There are exceptions, but that's the standard naming. Naming still remains the same for serial numbers, but naming has changed based on after acquisition. So it's like DCS 70 and 30, and then number of ports, then and FPGA. So the newer naming is also available. 7130L. So this is L and LB are the platforms that were launched after the acquisition. So these are fairly new, but still it's been, I think, almost 4 years. So these have the newer FPGA, low cost, low mux latency, optimized MetaMux and MetaWatch. LB is absolute lowest mux latency, more application capacity, so more modes. Optimized mux and custom development is also available. So when it means custom development, so customers can actually develop their own FPGA applications and run on our devices. So for that, we do provide a FPGA development kit. TAG doesn't mostly intervene in this. It's really worked with developers directly for account stream. But you should know that the customers do run some custom applications as well. Expanding list of 7130 SKUs. So this is the sheet where we keep all the 7130 platform information. So you can do just go 71/7130 hyphen codename, and it has all the list of 7130 devices until now, until L and LB. Any platforms later than LB, so most recently, which are 7130 LBR or 7130B. There are newer coming as well, 7132 and 7135. All of these you won't find them here. They are like on your standard Go code names platform on the where you have other DCS devices. So you will find them there in the about SKUs. You can just search like any other DCS platform or any other DCS or CCS platform. You'll find them here. You won't find them in this older sheets, but for some customers still have older K, E, L, LB series platforms running. So for that, you can refer this sheet. FRUs again. So what happens is any platform older than L and LB, you can't individually replace the fans and PSU. You have to when you are actually processing RMA. So it's written here. So the caveat is you can't for any platforms older than LLP, you can't individually replace the fans and PSUs, and all the platforms are end with hash, so they are not. They don't have PSU fan directions. So basically, they are kind of bare chassis. So when you do process RMA for these, you have to process RMA for the chassis plus the fans and PSUs as well individually. So you can't just process the RMA for the switch itself. And for that, also you can't include the part as individual fan and PSU. You have to use the kit names. So these are the kit names where you have basically two, I think it's two PSUs and 3 fans, something like that. So you can use this kit when you are processing an RMA for the bare chassis. This is only for anything older than LLB. So basically KCE and um, KCE. Even in that, some of them are also already end of life, so you can't really process RNA. But you'll know once, like when you try to raise an RMA for a device, you can just check if in the sheet down here. So if you see here individual parts list, there is fans and PSUs available. So if you don't see a fan PSU available for the platform here, you'll have to use the kit instead of instead of the individual parts. Any questions on this? Everyone's clear? That was all about the hardware L1 basically. Any questions until this point before we start knowing FPGA, what FPGA is and applications? So yeah, so as we have discussed previously that L1 switch, the 7130 switch is just not does L1 like a patch. It also has FPGA which adds more functionalities, more features, which adds so that can perform it. So it's kind of becomes layer 1 plus where you can perform more functions. And what we use for that is FPGA. FPGA means a field programmable gate array. Anyone wants to pitch in like what FPGA means? Anyone has any idea through their courses, college courses, what it is exactly?
Can't only go with the AGL app and stay on top of your
I think using the FPGA, we can just like program it in a way what like if you want to perform some particular action, we can program it, and after some time, if you want to change that particular action, then again we can reprogram that to one more action. So it gives that flexibility. Where I think when you compare with the ASIC, we don't have that flexibility because ASIC is like a hard code in that if any application, then that's hard coded in the ASIC, which you can't reprogram again. I think that's one difference I remember.
Anyone else?
I think for ASIC, right, each block can do specific function and we integrate everything. We capture. But then if it's field programmable gate array, then it's the same company which does the entire design for the entire purpose.
Okay. Yeah, so both of you have kind of gotten like the basic use case of it. So with ASIC, you have a fixed set of features, right? So you have, let's say, a 72 or 7280 or a 7050 device with SATA or SAN ASICs. They have a specific set of functionalities. You can do routing, you can do switching, maybe NAT, somehow TAPAC, but you have to have like specific features, and you can't really in the field change these features on the go. But with FPGA, you can with software logic, you can change these, reconfigure these chips to use for your use case specifically, as you want in the field. With ASIC, it's a limited functionality, but and that which you can't really change with software in the field. But with FPGAs, you can do that. So basically, a same chip can be used for, uh, like in this use cases, multiplexer. The same chip you can use for timestamping. The same chip you can use now for switch app, which can do now layer 2 switching, layer 3 routing, NAT, so different functionalities. And this can be changed at the way you want. So same FPGA, if let's say a customer has a switch, they're using it for timestamping, but now they don't need it to use for timestamping, but they have a use case now for L3 switching routing. So they can just install switch app, remove MetaWatch apps, and install switch app, and the same switch will start start doing L3 switching, L2 switching, and routing as well. So that's the base, like the use case. It reduces cost so that you don't really have to buy a new switch, a new hardware component. You can just reuse the same hardware for different features. So that's the real use case of FPGAs. The only drawback is like the capacity is not at the same level as ASIC, because ASIC have larger tables. So you have larger routing switching tables. That's not the same with FPGA. It will have limited capacity. So that's the only drawback when it comes to FPGA. Any questions? Everyone understood the use case, right? So basically, yeah, what we discussed. Reconfigurable, one switch can take on many functions, perform specific network functions with lower latency. Again, so because the ASIC has all these functionalities, it can have higher latencies compared to an FPGA. Examples would be TAPAC. An FPGA can do TAPAC. Basically, MUX is kind of TAPAC use case. Financial exchange trading, where again it can use for MUX, as well as timestamping, where in trading environments you do need timestamping of the packets, and packet filtering. So we have multi-access, which can be used as an access control list. So packet filtering is also possible using an FPGA. And plus, customer can use their custom applications for different use cases as well. So additional functionalities is also available based on the customer requirements. So this is a basic like architecture of a 7130L series switch. So you have front panel ports, cross point, again, the one that we've been discussing last week. Then the FPGA, which is connected to the cross point. FPGA itself has its own RAM. Then it's connected to a OCXO, which is a clock, which is used for timestamping source. JTAG is kind of an interface between the CPU and FPGA so that FPGA can be programmed. So JTAG is what is used to program the FPGA in the field. And you have 10G NICs that we discussed, the extra management ports that are available that are connected to the CPU. And again, the crosspoint also connected to the CPU through PCI links. Any questions?
Any reason why you have 10G NIC to connect?
Because we have 10G ports as well.
Okay.
So to take that, the 10G NICs, they don't only perform the connection. This is for BGP and multicast, which is used in the so that so basically in the trading environment, because FPGA can't run any other applications, like when it's running MetaVox or MetaWatch, it can't really run BGP or any other routing protocol as such. So we use Linux on the CPU and connect that through Crosspoint, so that the underlying Linux can run basic BGP and multicast and can be connected to the exchange. So for that application, you need the higher bandwidth things. So for that, this is a 10G NIC available. Yes. We'll discuss the how that is deployed once we discussed MetaMux and other applications.
Thanks.
Any other questions?
One more question. So the internal management ports, all the ports are 10G, or is there any 1G or something?
Yeah, there are two 1G as well.
Okay, so in the normal in any platform, it's like there can be two 1G and rest everything will be 10G. Is that right?
It depends on the platform,
Okay,
but
okay.
yeah, mostly two. I think most of the recent platforms, it's two of the 1G and then two 10G ports. That's like
Okay. And we can't do the BGP or PIM or on 1G ports, right? Or we
you can like the
Oh, you can
BGP
do.
is running on the CPU itself, right, underlying Linux.
Okay, so
Kind.
we can do it.
So
Okay.
you can use any port to do that, as long as it's connected to the CPU. As long as
Hmm.
the interface is connected to the CPU, you can run those applications, those protocols.
Okay, cool.
But
Thank
it's
you.
not really recommended because bandwidth again
Yeah,
drops.
understood.
Yeah.
Thank you.
Any other questions? It just discusses all the architecture in more detail. PGA transceivers connected to the crosspoint. You have Xilinx, two different Xilinx models, so L and LB. L has the 7P and LB has 9P. Fully user programmable, standard applications available from Arista. Plus, custom applications are also available. JTAG allows remote programming of FPGA chip, leverage existing FPGA development tools remotely. So basically, like from the CPU, you can program the FPGA using JTAG. RAM of chip, RAM is available use for FPGA. 4 8 gig DDR, these ACC chips. They have, I think, use case in MetaWatch specifically for the timestamping, but we haven't really gone too much in detail. But we have these four 8 gig of chip RAMs connected to FPGA available. Management processor x86 CPU, full access to underlying OS, all MOS features, packet stats, Ethernet command control of FPGA and PCI. So these are PCI links through cross points and front band ports. 10G management NIC onboard two 10G offload NICs for fast path to CPU based applications. The fast path and slow path, we'll discuss that once we discuss the applications. The BGP PIM, command and control, again CLI available. Precision OCXO clock, this is for timestamping. Precision clock provides a stable reference for MetaWatch or your own application. Atomic clock is optional, which is also available. If you can buy instead of OCXO, you can buy atomic clock as well, which is more precise. OCXO standard is there on L and LB platforms. Crosspoint is exclusive to every platform. This is like the main functionality of 70 and 30, so it's available for every platform. up to 10G connectivity between all components. Port mirroring application is possible through Crosspoint. And front panel ports.
Yeah, Advait, one question. So it was mentioned there that it's up to 10G. So we have like different platforms or different different cross points on multiple platforms with other than 10G interfaces.
No,
Is that
like, so the same can do like 10G, 1G, and 100 meg.
okay? So you can configure that.
Yeah,
Oh,
like
okay.
the Crosspoint can take the lower bandwidth, not higher, basically, like lower speeds.
Okay, so you can you can change the speed of the cross-point interfaces. Okay.
Crosspoint is
Cool.
kind of basically a wire, right? It's not.
Yeah.
It doesn't really take an speed is not that much important. Now, Crosspoint is basically a wire. And when it comes to FPGA, then there comes like if a 10G is supported or not, or 1G is
Oh,
supported. There
okay.
you have different speeds you have to consider if there's a DOIR supported or not. But with
Oh,
Crosspoint, it's just kind of a wire. So you
okay.
will support different speeds.
Cool. Understood. Thank you.
Any questions? We'll discuss all the applications now, like which are available, which we provide. Which actually, like earlier we provided, there are additional applications now, so which are, but so these were the original applications that were available. Metamux, which does end-to-one TAPAC kind of solution. MetaWatch, again, this is a timestamping app. Multi-access and MetaProtect, these are kind of packet filtering apps, which are kind of in your traditional sense ACL applications. And Exchange app is also similar to Watch, where you can do the timestamping, but you have other features as well available. Plus third-party applications where you have end user apps, so anyone can develop their custom application. Partner apps, we have some partners where we partner with them to develop custom apps for other customers. I think Enix is one of the partners, but I'll have to check the name of the company. FPGA technology, again, programmability, converged. This is available layer 1 plus switching devices, low latency, multi-feature determinism. Basically, like you can program the software to do whatever the switch wants, or the FPGA specifically. MetaWatch, advanced network monitoring and timestamping. So you can tap. So in MetaWatch also end-to-one is possible. In addition to that, the main use case is timestamping, but again, tap ag is also possible using MetaWatch. Picosecond precise timestamping. So you have timestamping that goes up to picosecond scale. Deep buffering is available in MetaWatch, 32 gig buffer, and multi-port capture. So basically, you can input multiple ports to the same MetaWatch instance. Protect firewall, it's not available anymore. Now, most of the things are run through multi-access. Protect is not really available anymore, but it's again ACL based filtering. Filter latency is 112 nanoseconds. Cut through filtering up to 510 rules per ACL. All these things change based on the application version, application available, and comprehensive logging. Again, but there are still limitations with logging as well, but you can log each packet that's being denied or allowed. That's available as well. MetaWorks, it's a TAPAD solution, data aggregation at low latency of 45 nanoseconds, deterministic, and then statistics also available. Multi-access, it's kind of advanced MUX. It does aggregation. At the same time, it can do packet filtering as well, and at the lowest latency of 95 nanoseconds. Per port filters in different data sets available. And also this is deterministic because it's a programmatic software, determines everything. Exchange app, timestamp insertion at the edge, remove network from source of latency. So basically this is directly connected to the edge where you can do the timestamping. Built-in monitoring and telemetry. So basically the monitoring is the stats and SNMP, other monitoring available. For telemetry, you have Influx as well. Most of these are app still available except for Protect. It's really now we are kind of moving towards multi-access more and phasing out Meta Protect because multi-access can provide the ACL functionality as well, plus aggregation.
So another question. These are all applications which are programmed on the FPGA,
We can program on the
but they are programmed on the FPGA.
Yeah.
So for the first one, deep buffering, when the FPGA is programmed for MetaWatch, where is this deep buffer residing?
I think this is the this RAM.
Okay, that's 32 GB. That's a lot of. Okay.
Yeah, 48 gig DDRs. Right? So that it will do.
Correct. Okay.
Yeah, for watch we need that much buffering because it's you can't drop packets when you're timestamping. So this is, and here we are also tapping. So you have multiple ports of 10 gig coming in, and there is only one output available, right? So deep buffering is possible when it comes to watch.
Do you also store packets with MetaWatch? Like if you want to review some packets,
We don't store any.
store just timestamp. But it can add latency, right?
Watch is not low latency application. Like we don't really advertise it or put it as a low latency application. It's mainly for precise timestamp.
And one more thing is we take the packets and timestamp it, but the data path continues. So these packets are separately tapped towards the MetaWatch application.
The copy is made.
Only the copy is
stored,
taken.
timestamp and stored.
Yeah, so that's
Not
where
stored, but yeah,
so
they're
the RAM,
timestamped
the buffer
and
and
you can send it anywhere you want.
so that's where that fast path, slow path comes in, right? So the data goes in through a different path, and this is a slow path where timestamping happens.
That's 10G per
Yeah. So this is kind of the FPGA connectivity, like overview. So you have ET ports, you have crosspoint, and this is like one instance of FPGA where you have 8 inputs and one output application port, which again connects to the crosspoint. So AP1 through AP8, these are all input to the application, and AP1. So there can be only one. So this is aggregation, right? Multiplexing. So there can be only one output port. You have that as one AP1 output port. And then you can have multiple, basically, instances within one. So this is one 8:1 instance. So there can be like 4 8:1 instances, depending on the FPGA. And then depending on that, there are different modes as well. So this is 8:1. There is like 12:1 as well, 48:1 as well. So that changes, that's different modes are available as well. We'll go through that once we are going through the application individually. But this is kind of the overview of how FPGA connectivity physically looks. Any questions in this? So the main point for here to focus on is all interfaces are just RX and DX lanes to the cross point, and user defines the mapping of ET and AP interfaces. And the commands are also very same. So if you want to send whatever is coming on ET1 to application 1, you go to AP1 and source ET1. Basically similar to what we did for the cross points. It's the same. It changes on EOS, so we'll discuss that later, how the commands change, how the port naming has changed, everything. But for MOS, this is how it works. So the logical connectivity looks like kind of this. You have transmit to cross point, to MetaMux, and then MetaMux to trading or wherever you want to send it. And then from trading to it comes, it doesn't go through the FPGA, it directly goes through the cross point to the servers. This is like the logical connectivity. It can be changed however you want, because lots of it is L1. It's basically it can be changed however you want. It's not the software that's determining. It's where you as a user can make changes as you want.
So what I understand is we are multiplexing data, right? And
Yeah.
we're sending it to the trade. So are we demuxing somewhere or
No.
how do we?
It's like trading. So we are taking data from different places and just sending it
Okay.
towards so there is no signal multiplexing, it's just packets and sending it to the trading, and then trading can take that however it wants.
Got it. Got it.
Installation, we have a separate slide for installation upgrade of app MOS. I'll skip this for now. But one thing to remember is each FPGA supports only single application. So basically, at one time, one FPGA can run only one application. You can't run two applications at one time on one FPGA. And almost all platforms are single FPGA, except for EH and LBR, where there are multiple FPGAs. But still, there is not necessarily like two applications can be run. It depends on the platform and the support availability. But most of the platforms, so the main thing to remember is this, that at one time, a single FPGA can run a single application only. Upgrade we'll go through that later on a different slide. Any questions? I think we'll go to Mux next time. It won't finish in
Yeah.
10 minutes. We'll continue the applications from the next session.
Okay, thank you very much, guys. So, in this phase one, we'll be completing MetaMux and multi-axis. So that also covers BGP and PIM as well. So, we'll be continuing it on this Thursday, Friday, and the next week as well. So, we'll be sending out the invites accordingly. Thank you very much for joining, guys. Have a good day.
Thank you, Advait. Thank you, Rajula.
And thank you very much, Advait, for the presentation.
Thanks, Advait. Thank you, everyone.
Thank you.
Thank you.
So when you say DP,
Stop the record.
I stop the recording.
I don't